Hey there, everyone. So in this video, I'm going to be talking about forecasting methods. So I'm going to introduce you to really cool open source forecasting tools, and these can be pretty useful if you are in e-commerce or any kind of marketing. So if you want to forecast sales, if you want to forecast revenue, you have to use some kind of forecasting method, right? So there are a lot of things in predictive analytics that you can use. Most marketers that I know I've seen marketers mostly use Google Sheets or Excel, which is also fine, but the problem is really not the tool itself, it's just the method that's being applied. And I'm going to introduce you to two methods, which just require some Python code, but it's not too hard to follow. So do follow along till the end of the video, and I think this can be mighty useful to you. So I'm going to quickly introduce you to these two without further ado. These are CatBoost, which is an open source high performance grading boosting library developed by Yandex. And so these are Russian, this is a Russian company. And so as you know that this is actually based on decision trees. If you have some sort of idea about boosting algorithms, XGBoost is another one. So even if you don't know, it doesn't really matter. I'm going to go from the first principles from scratch and just explain how you can use this method. I'm going to show you the code exactly how you can do it in a step-by-step walkthrough. And this is Facebook Profit. I've talked about this before in some of my past videos. Facebook Profit is also very useful. It is specifically for time series forecasting. So that's an advantage of this, but then it actually seems by comparing these two, which one's performing better. So before we get started, this will be a real data set. So this wants me to share the data set. I can't do that, but at the same time, um, feel free to follow along, take notes, and use whatever code you want to from here. Nothing proprietary about the code itself. I've just generated it you know using lots of different resources on the internet publicly available, and obviously apply some of my own thinking to it as well. But yeah, feel free to take notes and use it for your own project. So great, let's get started. The first things first. So what we're going to do first is run CatBoost. So CatBoost, like I said, is an algorithm. I just call it rating boosting algorithm, and we're going to try and forecast sales and revenue. We're going to look at the data set that we work on in a minute. But the way it works is that you have to install some dependencies, which are called packages and libraries. So we are first doing that. We're first upgrading and installing NumPy and scikit-learn. Scikit-learn is the one which helps us with some of the machine learning manipulations and stuff like training testing, as we'll see later. And then there is CatBoost, of course. So the reason why we do this upgrade in this case, as you see, is because there's actually a clash between some libraries and packages. So there's some requirement for NumPy if you have to use CatBoost properly, and that's stuff like that. So those sort of things have to be also taken into account. I mean, that actually took up quite a bit of my time in this project itself. So, you know, it's a good thing sometimes to upgrade your current installation of some libraries where there are dependencies that will sort of help, going forward as you run more code. So once that's done, you see what I did here is that I just ensured that NumPy and CatBoost from CatBoost to be also CatBoost regressor. Um, so essentially, there's going to be a regression algorithm going on behind the scenes as well, but we'll actually see what are the steps involved with that. And then we're going to use some accuracy metrics to see what kind of error is emerging from the models. So as you can see, mean absolute error. And then we can do search for the best parameters for the model using something called GridSearchCV. Okay. And then we're going to launch some more basic libraries and packages, modules like pandas and Seaborn. Pandas is for basic data manipulation. Seaborn and Matplotlib, as you will see, are for plotting and visualization. So now we uploaded the data set. As you can see, this thing called local data, ADC. And you will see here that these are the actual columns. So this is your first sneak peek into the data set, and it's probably as much as I can show you. But as you can see, this is weekly data, right? So we'll see in a moment that there are actually 70 rows of data. So I think that's roughly around half a year of, of data, right? So, or more than half a year actually, because a year probably has around, I'm sorry, not half a year, but 1.5 years, or a little less than that maybe. So 70 weeks of data, and we have, as you can see, 12, 19, 26 to 10. This is going on in that fashion weekly, right? And and we have total revenue, which is actually from all channels. We have Google Ad spend, Meta Ad spend, Google Ads impressions, Meta Ads impressions, clicks, impressions again, it's organic, and then we also have a seasonal component. So the data set that's actually something that you're seeing here, this data set is the result of some more EDA that's already been done on it. Okay, so some work has already been done on the data set in terms of extracting, for instance, the seasonality component, and that has been added in the form of an additional column. So if you plot the revenue, this is how it looks like, and you'll see that it drops off sharply at the start and at the end. So a very important step right at the beginning of this kind of analysis is to actually convert the week date, the date, the date column into date time format. This is very important for a lot of manipulations. And so you'll see once that's done, I don't know if it was done previously, it wasn't, but if previously it would have been done after directly uploading the data set into this environment. By the way, it's called Google Colab environment. So this is an online environment for running Python code, and it's free to use. So within that, I have loaded a data set. So once I loaded, if you've seen, you would see that big data was actually, I think it was in object format. Now it's in data, it's still format. Everything else is in float, which is like decimal points, and that's perfectly fine. That's exactly how we require it. So you see, this is our target variable. This is the outcome variable revenue, and the rest will be our regressors. And as we'll see, in this case, it's time series data, and we also want time itself or factors within time. Like if you break down time into say weeks, days, months, quarter of the year, stuff like that, then we can actually use that or those components of time as regressors as well. And we'll see that's been done. But before that, we actually have done another step. This is the step where we have actually dropped the first and the last rows from the data. And you see this is what followed. So that step actually followed from this simple visualization. But we quickly saw that there's actually a major drop. And the drop off is because there's no data before and after. From wherever this data was created. Uh, yeah, so there's some history behind that, but yeah, those data points are the start and the end of this entire data set, which is why it's good to drop it, because what happens is algorithms, any algorithms will actually pick up those as sort of indicators, and they will try to find patterns. Okay, so they'll try to see, okay, it might drop, okay, and they might try to make a mole out of a mountain out of a molehill. But it didn't drop actually, right? So there must have been data before, maybe not after, because till that point there was no data yet. That was the date um, up to which the data was extracted. That was the last date, the actual date on that day. But yeah, the point is it did not drop off, right? There would be data even after that. Revenue will still be generated. So anyway, after those 2 points have been removed from the data set, so as you understand, this was 70. So if I were to do say DF info now, it would actually get 68 rows. So now we see that we actually tried. So we do firstly a revenue over time plot. As you can see, it looks very similar to this, but it's just more, I think, better in appearance, and it shows a lot of data points on it, right? And then you see the extraction starts. So the extraction of the components, like I said, for the date and time. So you get the week, the month, the quarter, day of the week, year, like that. You get different components, right? And then you also you sort of do that easily by working on the data frame and then just apply certain functions to convert to extract that part and convert it into the relevant format. So here's the part which is already green, and that's because I've not used it. I have tried doing this. I tried to add additional lat features, as and also rolling averages as additional regressors. So I was trying out different things. I actually spent hours, many hours. Or you can ask me how much, because I was using, to be honest, CatBoost for the first time. I was hearing a lot about it. I've tried some other forecasting tools. I don't know if at the start I mentioned this, but Arima and which is part of the autoregressive group of models, and then there is maybe even light GBM, XGBoost. There are so many that are there, which are not just for time series forecasting, which are other purposes as well, general machine learning predictive models. But um, yeah, I mean, I wanted to try out CatBoost because a lot of people have spoken about it and said in recent times I've been reading about it that it's pretty good. I think it's relatively new as well, and compared to Facebook Profit, a lot of people have said that there are advantages. So I just wanted to put it into practice and see how it goes. Which is why I was playing around with it, trying as many different kinds of regressors and exogenous variables as they got, and see if they are going to add any time. But they didn't actually in this case. So these regressors in particular, I mean, so lag means simply a lag value of revenue. So revenue depending on its past values. And that kind of makes sense, right? You might be tempted to try this actually. It might not have worked in this case, might be working with another case as well. Because the outcome variable, if you can find some sort of relationship between the outcome variable and its past values, it's kind of like an autoregressive component, right? You can understand what it's in the ARMA or the ARIMA group of models. It can be useful, but in this case, that lag value did not have any I mean, they have a relationship to be there, but they don't have any positive impact in terms of its predictive quality, the predictive accuracy. They are not contributing anything else. Anything more positive. In fact, it actually deteriorated the model. Then you also have rolling averages, which is 3-week rolling averages for the revenue. That also, as well as for the other features, like ad spends, but that didn't help either. So I dropped it, and as you can see, these are the columns now, which includes the seasonal revenue component and also the daytime components and also the regular regressor columns. And then we actually use sklearn. Remember, I said scikit-learn is used for different kinds of machine learning techniques, and from there we are importing the training test bed. So this is an important part of any algorithm. This is where we split the data set into the training and a testing part. And generally, it's something like 70-30 or 80-20. I think we have done an 80-20 here, as you can see the test size, and 80% goes to training, 20% to testing, which simply means that you are going to validate. So this is the concept of validations that you are using out of sample prediction, and you're going to have accuracy metrics for the same. So it's going to be tested. It's going to be trained on 80% of the data set. 20% of it is never really seen, and we're going to use that as a test. So it's going to be like future data instance, even though that is already there, but it's still sort of part of the data set, and it's not seen the data set. Okay. And as you can see the features now, as I said, the daytime components, and then we have the regressors in this fashion. You can keep adding more regressors here, right? You also have the data for it. Outcome variable, target variable, total revenue. Then we do the train test split. And as you can see, shuffles false, which means that we don't want a random thing in this case because there's a time series component for it. And therefore, we wanted it to be, testing on the initial part and then rather training on the initial part and then testing on the latter part of the time series data. And then is the models and search grid search. So the model will have different hyperparameters. That's what machine learning models or other models have, where you have different kinds of parameters. So this is the set. That's what's called a grid. So depth is there, learning rate is there, estimator is there. Okay. If you want to learn about all the different kinds of parameters, you can actually go to CatBoost and just look at all the list of parameters, and you will get a pretty big list. You can see these are some of the common parameters. Random seed is there, loss function is there, bootstrap style is there, learning rate, depth. So many things are there, right? So you can decide which ones to use actually, which ones do you think will affect. And this is something that happens with experience. You apply more and more. In this case also, I was trying to find out, which is the best method to try and find the best way. So, for instance, GridSearch is like I said at the start, that this is the method to try and find out the best parameters for your model. This is a pretty involved technique. There are faster ones than this. There's something called a randomized search as well. So that's going to do a quicker search. So CV, by the way, is cross validation. So it's basically trying to validate using different kinds of um, you know different values of the parameters, and then trying to see which one is giving the best, going to be the best performance. So we do the we fit the model with the train and test data, and before that we have got a parameter grid using GridSearchCV, GridSearchCV, and the best parameters we just train them out in, and after that step. So the grid parameters, as you can see, 3 in depth, learning rate is 0.05, and n estimators is 150. Okay. Once again, if you want to read about these parameters, what they really mean, yeah, just go ahead, do a Google search, go to the official site or any authentic source, any good Medium article, whatever you get. Lots of resources available. I'm just going to give you the concepts here and how to implement it. It's a more practical video. So you want to make predictions now. That's the job, right? We're trying to forecast. So train prediction, test prediction, CatBoost predict X trend, CatBoost predict X test. So yeah, let's look at the predictions, and we have the evaluation now, and you can see mean absolute error. So mean absolute error is as it sounds. It's the absolute value of and then the mean over it of the basic error between actuals minus predicted. So the residuals, and get that difference here. So you can see that test is obviously better. That's always going to be the case. And I'm sorry, train is always going to be better. It's going to be some drop off in performance in test. So it's 85,579. Looks like big numbers, but consider the fact that these are almost in the range of millions. We're talking about weekly revenue data, so that's the absolute value that you're looking at. So considering that that's not actually big, we're going to see that in a moment. This is a plotting helper part where we define a function called plot predictions, takes in dates, prediction through level, pass those values, and then we get the actual plot. So we are taking, as you can see, the training period as well as the test period. So the training period is from the start to the length of the training period that we've taken, and it was so this is the test period that we are taking, right? It starts from that from the start of the testing period. So yeah, it's going to give us two charts then. And as you can see that in the first one, this is the training data, and you can see the true values given in blue and the predictions in orange, very close to each other. Very obviously, it's working very well for training. Let's look at how it's doing for test. Not so bad. There's just one section, as you can see, there's been a huge drop suddenly in revenue. Something to investigate for the marketing team and for the data team and the marketing team to work closely together to understand. But otherwise, you can see it follows the actual patterns pretty well, right? Pretty nicely. It obviously has some errors, and we can just look at that. So we're going to now again use scikit-learn, and we're going to get metrics from there, and from there we're going to have mean absolute error, mean squared error, R squared, right? And we're going to see how this model is actually doing in terms of errors. So mean absolute error, as you can see, mean absolute percentage error, as you can see, is nothing but the mean absolute error multiplied by 100. And so like I said, so this is the mean, right? Y2 minus y prime divided by y2, and the absolute value of it multiplied by 100. So similarly, you have formula for mean absolute error, and then R squared. And once we have that, we actually get the data. So you can see for train performance, obviously the mean error we have already seen is lesser. This is higher. And MAPE is also much lower for test, but it's around 13.44 now. 13.44 is not super bad. Ideally, it should be less than 10. We know that. But it's a good place to start. Maybe some fine tuning of type of parameters can be done. Maybe I'll make a video on that. But we've already done one step when you're doing something like GridSearchCV. You're trying to find out within the limitations of whatever you have provided, what is the best, so the data size, the data set, the features that you're using, all these things are there, which the GridSearchCV can't do anything about. But given those restrictions, given those current settings provided, things which have been provided to it, it has done its best job trying to find out the best parameters. right? And you can see that RMSE, of course, is root mean square. That's why it looks so big. Mean square also looks massively big. It's the square of this one edge at the top. And then you have MAPE as 13.44. R square is 0.5, which is, again, it's not very good. It probably should be, 0.7, 0.8, you might be wondering. So R square is what shows how much the model has been able to explain the variance in the target variable using everything that we have provided into the model. So maybe adding more features. So one thing that definitely happens, by the way, and I'll just add that. So remember at the start, I just said that we are using some regressors, right? So this is a time series forecasting. A lot of time series forecasting will actually use nothing but time or time components, right? Facebook profit is a good example. You often do it that way, but we'll see that we can actually use some additional regressors for Facebook profit too. Whether or not that adds value, we're going to see in a moment. But the point is that you can have additional regressors, and that's what we have done here, right? As you can see with CatBoost. Great. And my point was that if you keep adding more regressors, in most cases, you'll see that R square is, in fact, it's always going to increase. So R square is going to increase. But the point is, R square alone is not just the only good measure. You actually have to look at MAPE as well. Okay. So if you look at relative error, so we were talking about MAPE. So MAPE, you see 85,579. So how big is it? Like, that's just an absolute number because you don't understand it. You have to have some sort of relative percentage, right? And you see the relative percentage, that's how much it is, that's how much it is, that's how much it is to the mean of the predicted value or the mean of the actual values of test. Right. So these are the actual values of the test period, the actual revenue values. And if you take it as take the MAPE as a percentage of or not the MAPE, but rather the MAE, the mean absolute error as a percentage of that mean of the revenue values in the test period is coming out to be 10.12%. Depending on what are the goals, what are the kind of restrictions, what are the kind of expectations, this may or may not be very big. In my case, I don't think it's that big because we're talking about millions in terms of weekly revenue. And let's talk about residuals. But yeah, I mean, there's no room to be complacent. There's always room for improvement. Either you fine tune this model. Sometimes, to be honest, not every model can be fine tuned for a specific kind of data set, for the kind of complexity that it has. Some other model might perform better. So you might have to do things like running hybrid tests and try to do multiple kinds of models together and see which one is giving you a better result. So this is where we do the residual plot, where we actually have the residual between the test revenues and the predicted revenues for the test period. This is how it looks like. Remember, we had that weird sort of difference between real and predicted, and that's also been picked up obviously in the residual plot. As you can see, this it's in the negative because as you can see that the way residuals have been defined is it's y test minus test predicted, right? And you can see that the test predicted was actually lesser. The test predicted was actually more, right? And that's why you have the residuals as minus here. Okay. So we are also going to look at something called a features, importance. So feature importance is basically something that's very crucial if you want to take decisions as to what kind of variables to include in the MOM model. There's something that's been going on around this actually that I'm showing you. So that's, that includes say marketing mix modeling. And I've also been trying to think of what kind of variables to look at. Okay. And this is actually a very good method of doing this. So you see that chat value is a very nice feature importance visualization, feature importance sort of analysis methodology. And this is how we're doing it. We're doing a simple waterfall chart plot. And this just shows you on the right hand side, it's red. Red means the positive contribution, right? And larger the red bar, it simply means that it's adding that much positive value. On the other hand, if it's blue, it means that it's taking away value from the, so its contribution is negative. So you can see that the Google Advertisement has positive and impressions, Google search impressions, month, the component of daytime month, that is negative, and a few others are positive as well. And this is another visualization. So by the way, this particular one was for one prediction. Okay, so this is for the I equal to 5th. All right, and as you can see that it's during the test period, it's taking the feature names for the 5th row. All right, and that's trying to grab its value and the SHAP values for it. This one, on the other hand, this is an overall explainer for the CatBoost model, and we're going to use the entire data set here in this case and all the values to give a summary. So see Meta ads and Google ads, very similar. It's not changing too much from that one thing that we just saw, but yeah, you can still take a look at this, and this is going to give you a very nice indicator of what variables to actually consider. So we see that, not surprisingly, the spends are important. All right, they have the best or the most important. They are the most important features as part of this analysis. Then we can actually look at the number of times. So we saw, remember, this was one prediction. So you can actually look at this for a number of predictions and see how many times in this different calculation for each of the rows, there's actually a positive value or negative value for a particular feature. Okay, and we are talking about SHAP here. SHAP is the predicted or the observed, contributions to revenue. Okay, so there you go. Positive is SHAP is greater than 0. Negative is SHAP is less than 0. So SHAP is nothing but it's a data frame that consists of SHAP values and columns from X list. That's pretty much it. And we see again, there again. So we see mean SHAP value. These are the highest ones. Meta, followed by Google, then some yearly components and all. That's it. And impressions is actually below here as well. That's the organic. And this is another one. So we continue with SHAP, and this time we're going to see it in the form of a bar chart. And then we're going to see which ones are having the highest mean impact on revenue, right? So there you go. Meta ads and Google ads right up there in positive, and right down there some negative. So don't take too much, look too much into it, read too much into negative contributions, especially when they have, these kinds of things like set time. And they will probably have some sort of distorted effect on the overall calculations or analysis, because it's not really a proper regressor in the sense, right? So it's probably best not to look at these time components, especially if they're giving negative calculations. All right. But yeah, I mean, remember in this case we also have seasonality components separately. So do take a look at that. So you'll see that how many times that it has actually given positive contributions, given around 6 times, but it's around 8 times that it's given negative contributions. So this is also very useful chart. Now we come to phase profit. So we have seen one particular predictive methodology. We have seen CatBoost, how we can use it to carry out carry out forecasting very nicely, and I think pretty easily if you have been following me. If you put some effort into it, I don't think it's difficult, and I do not think these will stand to benefit a lot. They can stop using unscientific methods which are too basic, too rudimentary, and don't go into the details. Don't go into the complexity of the data set in order to make the predictions. So now we're going to talk about a prophecy, right? So it's profit. So let's listen to what the prophet is saying. So it's a pretty small piece of code, you'll see here. And what we're doing here is again doing the same thing. We are actually preparing, we're getting some important packages and libraries. So for profit.diagnostics, we first pip install profit here with Google Colab. We actually, from profit, we import profit. We have profit.diagnostics. We import cross validation performance metrics from there. That probably went pandas we actually have done earlier. And then we have the different columns, right? And we see that we are using the basic data frame that we have, we're using data for, and then we are just including all the regressors within it, right? And so this is how it has to be done. It has to be in the form of the data time has to be DS, and then the outcome revenue, the outcome column equal to revenue for 6 in this case is going to be Y. So DS and Y is the naming convention. Split it into test and training. That's how we're going to do it, right? So it's been hard coded as 13, by the way, but this can easily be done in the form of percentages. We saw that there's actually 65, 66, or I think 68 rows. So from there, 20% comes out to be 30. So yeah, that's how we've got this 30. And then we get to have seasonality as false, and we can use any kind of value or any kind of seasonality, and we can just set that value here. And we have the regressors, right? And then you have rig and regressors, profit model, add regressors. So this is important. Add regressor is important. Otherwise, you won't be able to add external or additional exogenous regressors. Remember, I said at the start that predictive profit is primarily it's primarily meant for forecasting, and it's primarily meant to work kind of like dependent only on time. But there are these additional features as well. So you can add regressors. Remember, I'll also point out at this juncture that I have tried it in several iterations of it actually. One of those was to not include any kind of external regressors. And to be honest, we'll just see in a moment, it doesn't quite help. At least in this case, I mean, again, I won't be generalizing. Makes no sense. Different data sets require different kinds of approaches. Not every model is going to work everywhere equally well or equally bad. So yeah, something you have to test, but it just gives you an idea what are the kinds of things that you have here, what are the kind of opportunities, what are the tools that you have at your disposal, and just make the best use of it. So you predict it on the full data set, and then you have split it, and then you just plot it, and then you have your y hat, which is your prediction values, right? And then you do a cross validation. So its cross validation method is typical. This is unique to Profit. So you have to know the syntax. So this is the initial period. There's an initial phase. There's a period, all right, and then there's horizon. I'm going to show you in a moment, but let's actually first look at outputs. So this is what the training looks like. Okay, so the training forecast again, very good, right? Training is always very good in most cases, unless there's something super wrong about model and its configurations. And then you have test here. At first glance, if you ask me, this looks better to a certain extent, and that's because of the huge sort of, I don't know if it's under or over. Yeah, so it is overestimation for a period, right? For this period here, which during which the revenue has dropped massively. So compared to this period, I look at this period, it doesn't look that bad. But overall, you'll actually see that profit is done worse, right? Even though it's meant to be the specialist in terms of time series forecasting, right? It looks better, doesn't it? Somehow, I mean that's just a visual estimation. That's why it's not enough to do visual estimation. So by the way, this is the test period visualization, and we can actually look at this cross validation performance metrics here. Okay, so horizon MA, so for different horizons, all the error metrics have been given here. So these are the different cross validation syntaxes. So you have to remember initially is how much data has been used for training in the first fold. And so fold means, you have cross validation in multiple folds, right? You have different sections of the data, apply the test here, and then you have another data, and you must move forward or backward. You have to have some methodology for choosing the next data set for testing. And that's how you do it. You start with an initial, and then you have a horizon, okay? And horizon is how far ahead the model forecast in each fold. Okay, so horizon is 7, it means you're forecasting for the next 7 days. It's that simple. And then it, how much it shifts forward to start the next fold for the next test. When it's going to retrain and it's going to be evaluated again, that is what is given by period, right? So that's the definition for it. That's not supposed to happen. Yeah, so that's one of the cool things about Colab. You can actually copy paste images. So that's what it was. Yeah, there you go. So I hope that was clear. Now we're going to actually look at the metrics, because we just can't look at output. We actually have to look at the accuracy metrics as well. And we're going to look at that. We're going to look at again mean percentage absolute error, mean absolute error, and compare and extract. Just compare and extract. So the true profit, predicted profit. True profit, as you can see, is during the test period, the forecast during which is y. And we evaluate it, and then we see that MAE is 126,400. Remember that was something around 85,000 for CatBoost. So it's more in profit, which means it's worse, right? And R square is also lower, much lower than that. It was 50%, somewhere around 30%. So this model is only able to explain 30% of variance in revenue. And this is after adding additional regressors. And I'll tell you that one point I don't think I completed the sentence after starting. I had run this profit model on this exact data set, keeping everything else same, just by using time as regressor. Haven't added the additional regressors, the exogenous variables yet. It was still 0.3, very similar again. So my point is that in this case, at least, adding additional regressors absolutely doesn't have any kind of value. I'm going to explore that more, why it is happening, and I'll try to share it with the community with you all. And if you have any ideas about it, you can also share what's your experience with it. And then I'm going to plot residuals at the end and just show you that, okay, so yeah, there was actually a major period where it's overestimated. And yeah, very good. Right. So this is the period you can see between say 15th of Jan to start of February, and there you go, 15th of Jan to start of February. That is around the period where the interest rate regulatory year where we saw a huge amount of overestimation by profit. So this is the comparison that I was talking about. I definitely encourage more marketing people not to be scared by our code here. It's pretty intuitive. If you get the idea, it's not very difficult to implement. More than happy to sort of talk to you and help you out if you have any kind of questions, if you want to learn more about it, if you want to learn about what kind of resources, what kind of sources to go to for learning, you can reach out, you can comment below. But yeah, hopefully this was useful, and thanks for watching. And yeah, I'll see you in the next video.